right? So this is the natural process that is going on everywhere. So landslide is one of that part. And when it interferes with our lives, and we know how much the economic losses, the loss to habitat and environment is there. So what happens if you have a mass of earth material or rock that is under the influence of gravity? Gravity is everywhere, and that gravity pulls that towards its center. So you can see, if you see the global landslide event from 2004 to 2016, you can see that India, China, particularly India and China, uh, the number of landslides events are higher than the rest of the world. And out of that also, if you categorize the illegal hill cutting, the construction related landslides or slope instability, the mining related slope instability, that also the India and China, they are the number is much higher, right? So of course we are a developing nation, we are developing, there is need of construction of infrastructure, so it may happen. But okay, we have to do in a judicious way for any hill cutting or construction activity or mining, so that this can be reduced. So the anthropogenic landslides that contribute on a major part of this landslides that is occurring, and out of that 28% is construction related. Like you have road cut slopes, you have railway cut slopes, you are building in infrastructure, then 12% are mining related issues. Okay. If we see the landslide susceptibility map of India, you can see that almost 15% of the area is affected by landslides. And we can see the Himalayan range, particularly starting from the Jammu Kashmir, Himachal Pradesh, Uttarakhand, Sikkim, and the northeast region, they are prone to landslides. And you can see the Western Ghat also in Maharashtra, Pune, in Karnataka, Kerala. In recent times in Kerala, you can see the number of landslides has increased many times. Okay. And you can see you can see there is part here around the border of Odisha and this Andhra Pradesh, that is in Rayagada, Koraput district, and the adjoining area of this one in Andhra Pradesh. They are also susceptible to landslides. Okay, so many times you must have heard news about, okay, in Koraput railway track, boulders came down on the track and there is a traffic issue. Okay. Even in during the extreme event like cyclones, there are many landslides in Gajapati district of Odisha. Okay. But yes, the report of landslide in Odisha is less. Of course, we have many landslides. Because of that, I think the area shown here is less, and it can be with research, with our data, we can properly evaluate this area, and there is a great opportunity here to do work on landslides. So again, come to this landslides, how to understand these landslides. So as I told you, okay, you have a slope, you have some material over it, and it slips, right? So when it will slip, we have a gravity, okay, that is acting downwards. And this gravity has two components. One is shear component, another one is normal component. And this shearing component, this shearing force that gives the shear stress and wants to pull this material along the surface, right? So this becomes my slip plane along which any material that will fail. And if this shear force is more compared to the resistance, it will fail. So what will happen? You have the shear force in this direction, then you have normal force this one, and the normal force, there is a friction here. So what will happen? There will be a friction times your normal force that will resist this one. So the cohesion and friction between these materials, that adds the shear strength of the material. So we have shear stress, we have shear strength. So when this accumulation of stresses, shear stress is more as compared to the shear strength, it fails. So if I give a number, let me do it like this. I have I have inducing forces or inducing stresses, that is the shear stress, and I have the resistive forces or resistive stresses, that is the shear strength. So numerically, if let me give a number, that is we generally give, that is your factor of safety. We put that is factor of safety. So we tell that okay, that is factor of safety is the ratio of your resistive forces, okay, resistive forces divided by your driving forces, right? Or I can in terms of stress, that is the shear strength upon shear stress. So if factor of safety of any material is more than one, we'll say okay, this slope is stable. If it is less than one, then okay, this slope is unstable. So what is happening? As I told you, once you increase this shear force, and if there is any means the friction and cohesion is less, then there will be instability. So this is the shear component. This is a particular slope. Let me make it a slope like this. Here you can see the shear force is increasing, right? And you can see the normal force is less. So the resistance is mu times normal force and the cohesion. So we have what we have? We have this, suppose tau is shear strength. So this shear strength is provided by cohesion C, plus you have the normal stress that we have, then tan phi. Right. This is my friction. This is my cohesion. So this cohesion and friction, this contribute to the shear strength of the material, and this component that we are seeing, that contribute to the shear stress of acting over there. Okay. So in order to destabilize the slope, I will say the cohesion will be reduced, the angular friction will be reduced, and then there will be sliding. Okay. This is the basic. This is the basic. Okay, and that means this is the equilibrium between the play between different forces or different stresses that is acting over any earth material. Okay. Let's start about how do you classify the landslides, right? So we classify the landslide on the basis of the type of movement of the type of material that is used. Okay. So we must have heard, okay, this is a rock slide, this is debris slide. Okay. So what we will see, what is the nature of movement. So nature of movement is, suppose it is a free fall, then we'll use fall. It is toppling, means there is a block of rock which will rotate and fall, right? That is toppling. Then slides, simply it will slide over the surface. If it is a planar surface, then this is translational slide. And if it is rotational, the curvilinear surface, then the movement will be rotational, that is rotational slide. Then you have lateral spread, the material will spread out from the origin. Then we have approach, means if the water will be more, then it will flow like a viscous fluid. And we have complex type of movement, means everything is there, combination of two or more principal type of movement. So this is the type of movement. When we are certain, okay, this is the type of movement, then you use the suffix, what is the prefix, what is the type of material, whether it is a rock or whether it is engineering soil. Means in soil, generally in engineering, geology and rock mechanics, we tell if anything, the strength is less than 1 megapascal, that can be treated as soil or debris. So if you have predominantly coarse fragments of material, okay, particularly if I will say sand and cobalt, boulder, pebble-like material, then we call this as debris. And if you have silt and clay type material, then that is your predominantly fine material, that is called earth material. So we have rock, we have debris, we have earth. Earth means the finer materials, more than 80% finer. Clay size particles are there. So we know movement, we know this is the type of material. Then we say, okay, if there is rock involved and the movement is fall, then it is a rock fall. If it is a predominantly coarse fragments of rocks, that is the debris, and the debris is falling, that is debris fall. And if it is very fine particles involved in falling, that is earth fall. Similarly, for toppling, you will use rock topple, debris topple, topple. This is how we classify the landslides. And if you can see here, um, you can see here that, okay, there is fall, the rock is involved, the material will directly fall over this. This is rock fall. And the debris fall is like this. Let me how much time I have actually?
1 hour, no problem.
No problem. Na? Okay. And if anyone has any doubt, even during the mid of presentation, please ask questions. Your question can be in any language. Any language means I can understand Hindi, English. So don't hesitate in any of these three languages, right?
Okay.
To ask questions. I will be glad to address. ଓଡ଼ିଆରେ ବି ଆପଣ ପଚାରି ପାରିବେ, there is no problem. Science there should be no barrier in language when you understand any phenomena of science. Right? So you can see I was talking about this toppling. In toppling, what happened? You have a rock, okay, you have a slope, and these are the joints. These material, they will topple, they will rotate and fall. Okay. So you can see once toppling is there, then we go, okay, we have a rock is topple, then rock toppling, right? If you have debris topple, then debris toppling. You can see these earth topple or earth fall. Generally, you can see this happens during the flood time, right? The river bank collapses, right? So simply it may slide or it may topple like this, right? So that is your example. I will say that is an example of this earth topple, right? Okay. Then you have slides. The entire mass, you can see they will give this rotational feature. This leaf surface is rotational, and the movement is rotational. Like it will go like this. So that becomes a rotational slide. If you have any planar features, okay, and there is a plane, weakness plane, which acts as a slip surface, and the material slips, that becomes the translational movement. The linear movement is there. In rotations, you have linear and rotation both are involved. In translations, you have linear movement is there. Right. In spread, suppose what happened? Suppose you have a competent rock over here, and you have an incompetent rock over there. Incompetent means the rock is, I will say, suppose a strong rock. Suppose let's example of a sandstone which is jointed over here, and you have a clay below the shell or anything. So with the percolation of water, because you have joint, if there will be any percolation of water, then there will be swelling, then the plasticity in the clay increases. So what will happen? It will start to flow. So whatever the material above it, there is any competent rock, then it will spread out, right? And in flow, the water is very high, right? And it will take away the rock and debris and earth material, and it will flow. It's just flow like, I will say, flow like a river, right? So these are different types of landslides that we categorize on the basis of movement and the material involved, right? And sometimes landslides are very slow, and sometimes landslides are very, very rapid. In slow-moving landslide, okay, you can predict and you can avoid that landslide. But sometimes it happens if you get rock slides, it gives a very minimum time to escape. So there is a need of the hour to create any early warning system, so that the prior information can be given to the stakeholder and proper mitigation measures can be taken. Okay. So I told you about this, how the rock fall is happening. This is a free fall. There is no contact. Something overhanging mass is there. It will directly fall on this one. Then you have a toppling. There is rotation and fall. Okay. Then there is sliding. This is a sliding of the entire mass. Okay. So generally, we see typically this type of sliding in Odisha. Okay, because the debris involved, the lateritic soil is involved there, and rockfall incidences are also there. Okay. So we all know about the discontinuity that is present over rock, right? You have different joints, then we have fault planes, joints, collision planes, right? So they also interact many way. They induce instability that is structurally controlled instability, right? So we have, if we have a slope and we have a joint plane, and this joint plane is dipping gentler than the slope phase. Slope is steeper and joint is dipping at a gentler angle than the slope phase. Then the entire mass, because we know in joint, because this is a jointed rock, if there is a joint, the cohesion and the angle of sections or the shear strength along that plane will be less. So this becomes my probable plane of failure. So what happens? If I have a joint like this, as it is gentler, then the slope, this mass can go down. If I have a joint which has more deep, which is dipping more than your this slope phase, then it will not get the free space for the movement, so it will be stable. So gentler joint than the slope phase will be your culprit here. Okay. So similarly for wedge failure, two or more sets of joint, they will intersect, and the intersection point or the hinge line, if that the deep is gentler, then this wedge-shaped block will slide away, right? Similarly, in case of toppling failure, as we have discussed, what happens if you have a slope and the joints are dipping in opposite direction at a high angle, then there will be rotation of the block and it will fail. Right? So these are few types of landslides. Okay, there are many on the basis of, again, on the basis of the velocity of the movement of the material, rapid, extremely rapid, very rapid, like that, on the basis of the velocity of material involved in classifying the landslides. Okay, so everyone is, I hope the students that have the, of course, if you are from geology or geophysics background, you can understand these deep joints and fault, and probably the other discipline, if they are facing any difficulty in understanding, they can ask me a question to clarify. I will like to clarify that. You can see this is another example of rockfall. If you have, suppose in coastal area you have a rock cliff like this, so this current will erode the base, right? Then this will be a overhanging mass, okay? And if this joint overhanging mass, when the shear strength will be reduced, this will fall, and that will create rockfall. Okay. These are few examples. Mainly, I have concentrated on the examples in the analysis so that we will get idea how we study these landslides and understand the landslides. Okay, then we can think of doing any kind of further study on this part, and that will contribute a lot to the society. So these are examples of this. I will say along this river Ganga from Rishikesh to Deprayag. Okay, so we can see how this rotational slide I was talking about. You have debris here. You can see sand, shale, boulder, all these things, and you can see a circular surface here. This is also a circular surface. So this is a rotational slide that is along this one. And because of this, whatever retaining wall you have put on this, and they got damaged. Okay, and you can see this is the river Ganga, and this is the road, and this material has gone down. So these are examples of your rotational slides. That is example. I will also give you examples from Odisha. So you understand what is the landslides, what causes landslides. Then we see what are the factors that controls the landslides. So we have to do, okay, I told you there are certain forces, certain things which drives or which induce the landslides, and there are certain things which resist the landslides. Okay, so if you have material characteristic, okay, so if you have a very high strength rock, granite basalt, and you have a very weak rock, phyllite shale, then we know, okay, the material characteristic will be different. Okay, suppose you are making a slope of 70 degree in a basalt, okay, it's stable. But the same thing, if you will do for phyllite or if you do for any slate, shale, I will say, then that will not be stable. Okay. So the driving forces means the slope angle. Once you increase the slope angle, it will induce the driving forces. Means the shear component will be more, right? So it will again induce the instability. Then what is the control and resistance? The control and resistance is, okay, we have friction that is acting between the material, right? Suppose I have I put, okay, this is my rock. So the friction that is existing between this and the cohesion of the material, that is important. Okay. So if anything, if I have to check what is the friction between this and this slip plane, right? What is the friction between the grains that is existing? Okay. A plastic medium, or will act if there will be any water, will there be any stress, will it do it? It will so quick moment that I will see. So these are the landslides. Many cultures on a part of the space moment we have the interplay with as human beings. The human beings they destroy the environment many times. Okay. So we have natural causes. Of course, there are naturals because we know that this is a mass wasting process, and in mass waste that has happened. So might be that's why we are here. Okay. Without mass, if there is no agents are there, suppose I will say there is no wind, there is no water, nothing, then there will be no mass wasting. So our class is natural, but I have to mitigate because I am constructing something that we call that may take the lives. So then there is natural cause and the anthropogenic. Natural, we have inherent parameters and we have external parameters. This external suppose you say, okay, particularly in India, if you say during this monsoon period, you can say the landslides are more. So we'll say this is triggered by the rainfall, okay? Because once there is more rain, then I will discuss it later. What happens when there is more rain? Then it fails, right? So this external factor that triggers the relent, or we call it as triggering factor. We have seismicity if you have earthquake, okay? That also uh, do the instability to the slope, and the slope fails. So seismicity means the earthquake. Earthquake, what happens? You have the acceleration, the peak ground acceleration will be different, right? And one component slope, one component will failure, and once there is a plane of failure in that directions, then this will add instability. In inherent character, we have lithology. What is the rock types? We have structure, means whether are these jointed rock, are they foliated, right? Either any fracture present over there, either any fault damage zone. Okay, that is your structure part. Then you have slope. Slope means the inclination to the surface that we have. That is your inherent parameter. Then the relative relief, which I will say, okay, if relative relief is high, the slope will be high. Then the land cover, whether this is covered by any forest or if this is barren land, that also influences these landslides. Okay. Then hydrogeological conditions. Hydrogeology means your what is the water inside that? Okay, each when there will be water and rock interaction, the strength of the rock decreases. The water itself creates pressure that is known as water pressure or field pressure or pore pressure that contributes to the landslide. Right. Then anthropogenic causes. In anthropogenic causes, you have deforestations. Okay, you are if you are cutting trees, you are removing forest, then there are chances that there will be landslide. Because what happens? Suppose you have soil or debris slope, and there is vegetation over there, right? So if the vegetation, if there is a vegetation, then it holds that rock soil mass the surfacial. Landslide. Then improper land use. Suppose this is the landscape, and here there should be no construction, but you are doing that. And when you are doing any improper land use, if you are not doing it properly, then the interpretation, the slope angle, so that changes. Okay. So we'll see. I will give few examples. In terms of few examples, you can understand. I have many photographs to show. From that, we'll see all these things. Okay. So what we have? We have these properties, the inherent property that we are talking, lithology, structure, slope, all these things. Okay, that is controlled by the geology of the material. So we have what happens? We have rock and rock mass. The difference between rock and rock mass means I will go to this slide probably. Yeah, you can see here what is happening. You have a because you can see if I am taking a piece of rock from this one, so that becomes intact rock. This is devoid of any fracture. I'll pick okay. Suppose the size of the rock is, suppose I am taking a specimen of 5 centimeter to 2 centimeter, 10 centimeter. That may be devoid of any fractures. Okay. So microscopic fracture may be there. The major and major scale fracture will not be there. So that can be treated as intact rock. Once I increase my observation, increase the area under which the rock might be studied, you can see once I increase, okay, there is one set of joint, then there is two sets of joint, then it gets fractures. There are many sets of joint. Right? So the heterogeneity comes into play. So initially we don't have heterogeneous here, then the heterogeneity comes into play. So the landslide it's not an intact rock failure. It's the whole rock mass that fails. So if I study the intact rock, suppose the strength is this, obviously there is no fracture there. Once there is no fracture there, the rock may be good enough. Okay, I will say this should be stable, but that is not the case because landslide involves a larger mass where discontinuity is there. So we have intact rock plus discontinuity that becomes the rock mass. Okay. And that rock mass is responsible for the landslides. So there are many, we'll see, in rock mass we have different minerals, okay, and the distribution is different, okay, you have joints, right? So all these influence the lithology and the stability. You can see these photographs, you can see, okay, you have different layers of rock, right? Might be this rock is strong enough, but this seems to be weak, right? This rock seems to be weak. So when I evaluate this slope, I have to, okay, this is a different rock types, means I will treat this as a different rock mass. I will treat this as a different rock mass, right? So once happen, if the rock mass, we know the strength is weak, so there is chances it will fail. Once it will fail, and you can see the rock above this.
Excuse me, sir.
Yes.
Sir, will you please come back to the intact rock again?
Yeah.
Yes, sir.
Okay. Yeah.
So here the intact rock means the density of the rock or something else, sir?
No, it's not density of the rock. You see, suppose there is suppose you want to build a tunnel. Suppose you want to build any slope, right? And what happens? Suppose for the lab, I will bring a small piece of rock, right? So
Yes, sir.
that is devoid of any fracture. Okay, I'm bringing a small piece of rock that is devoid of any fracture. The lab is I want to do, right? So it may be, suppose you take a 10, 12, 30 centimeter rock even that is devoid of any fracture. So I will say this is the intact rock. There may be micro fracture, but there is no major scale or major fracture is there, right? So I will say, okay, this is devoid of any fracture. So this can be treated as intact rock. But you see, once my observation, because what happened? Suppose I have, let me draw. Suppose I have joints like this, right? I have joint like this. Suppose there are two sets of joint which are here. If I will take a sample from here, right? So this is my intact rock. This is devoid of any fracture, right? If I increase my observation and I will take a sample from this is my, there is a fracture. If I increase my observation and I will take a sample from here, the intact rock is this one. What any fracture? The rock mass is my intact rock.
So that means the sample which didn't have any fracture or joint present, that means that's one the intact rock.
That
Okay, thank you, sir.
is correct. Okay. So if you have I'm going very the landslide. Suppose take an example here. Though it may take more than 1 hour. Is it okay, Professor Rasim? So
Sir,
suppose it's fine, no?
it's fine, no problem.
Okay. You can see. Suppose this is a slope, right? And this is if this is intact. Okay, this is stable. Let me introduce a joint here. Simply a joint, introduction of this joint. If I'll test this, I take any sample, I test it. I took the sample from here, I took the sample from here, and I test it, right? So what will happen? Once I test it, it gives good value. Suppose rock, let the rock be granite, right? The strength is quite high, it will not fail, right? But once there is introduction of this discontinuity, and in granite there may be joints, right? So what will happen? Though the rock itself is strong, with the introduction of this discontinuity, this mass may slide. Right. So I have to study what is the influence of this joint on this intact rock. So then becomes its rock mass, rock plus the discontinuity that is present over there. Right. So we have different tools, like we have RQD, rock quality designation, which takes into account of the fractures. We have rock mass rating, we have slope mass rating, we have Q system. Okay. So these are few systems. There are many that evaluate the rock mass conditions in different engineering applications. Right. So in this case, I was talking about, okay, if you have different rock, so I'll treat this as a different rock mass. I will treat as this a different rock mass. I will treat a different rock mass. Right. This distinction, I will say, okay, in this slope, the rock mass here is different. The rock mass here is different. The rock mass here is different. Okay. So once that is, suppose this becomes the rock mass is weak. Okay. So it will fall. Once it will fall, you can see there are joints. Then these blocks they will freely fall. Then we can say, okay, there is rock fall. Rock fall activity will be there, right? And we know that with time there is weathering and different rocks. Okay, they depending upon their mineral constituent, the degree of weathering will be different. Some are very durable, some are less durable. If you have more quartz content, that is more durable. And suppose you have quartzite, there are chances that it will fail less. And if you have any clay minerals, then like spectite, halite, all those things, then the chances of failure is more. Right? So we know, as I discussed about this intact rock and rock mass, okay, rock is made up of minerals, right? And no rock can be stronger than minerals, and no rock mass can be stronger than intact rock. The mineral is the hardest in terms of the, I will say, if you compare with the minerals in tetrock and rock mass. Okay. So just by doing analysis of, okay, this is the minerals, we cannot say, okay, this slope is stable. Right? We have to see in a holistic manner. We have to see, you have to observe, okay, the discontinuity should be taken into considerations. Okay. So that is how the lithology influence, and the types of mineral is also important. There, suppose you have gypsum, we have limestones. There is solution activity, there is solubility, then there will be carbon, there will be the material will be go away, then it will create voids, and it adds less strength to the rock. Okay. Suppose you have evaporates rocky salt, then under pressure what happens? They flow like plastic manner, right? So this gives problem in particularly in mining and tunnel. You are creating a channel, right? You are creating an open space to excavation, to excavate the rock for your tunneling activity or mining. But because of there is a rock salt. Okay, so what happens if there is a rock salt? It will flow plastic manner. You want to make, okay, this is the dimension of the tunnel. Suppose I want a 5-meter radius tunnel, but you excavated it, and with time there is a rock salt, and the rock salt will come into this, and there is a squeezing, and your tunnel is around, suppose I will say 4.5 meter. So this happens depending upon different lithology. Similarly, we have different rocks. We know that there are igneous, metamorphic, and sedimentary rock, and they have different properties. They have different orientations of mineral. They have foliations, and these add instability to the slopes. As I am talking you, okay, you can see how the mineral constituent in the rock is influencing. Suppose you have, I told you earlier also. Sorry. So you have a strong rock above this. You have an impermeable rock, argillaceous rock below this. Okay. So what will happen when there is infiltration of water? Okay. Then this will flow. The instability will occur at this point, right? Then once there is a movement of this layer, the weak layer, it will take away the massive of it. Though it is strong enough, it will slide. It will go like this. Okay. So we can see just by suppose there is something. We will say, okay, this is a strong rock, so there should be no sliding. But once you see there is sliding, that means beneath this there is something. So we need to know. We need to know the surfacial activity. We need to know the underground geology of subsurface geology, so that the entire process can be understood, and accordingly we can mitigate the things. So why this? I will say the geology or this geology is important. It gives the very cause of landslide. Okay, and that if that is addressed, then we can think what should be my mitigation procedure. Okay, so if suppose I will say if we could not understand what is happening because of this rock mass, what is happening because of the subsurface geology, then our mitigation measure may not work. So that is very important. The role of geologist is very important, right? He or she addresses the very cause of the landslides. Role of structure. So we have discussed role of structures means if you have joints, faults, then that has influence on the rock mass. So that need to be evaluated. What is the rock type? What is the orientation of the bedding surfaces? Is there any lithological contacts? Whether this is unconformity is there, whether the beds are conformable, what is damage zone, what is the joints, what is the faults and shear, is there any damage zone? Because of this damage zone means, suppose there is a faulting, then the core of the fault that will be more damage as compared to the as you move away from that core, right? So that becomes your damage zone. Okay. So that need to be identified. Once you identify those things, because there are I can say there are landslides. Some are structurally controlled, means because of the discontinuity. This discontinuity plays significant role, and it might happen the rock mass itself is very low, the strength is very low, and that causes landslides. Right? So we have many types of discontinuity. One is integral discontinuity, then we have this mechanical discontinuity, right? In integral discontinuity means you have certain cohesion is there, right? Suppose you have bedding planes, means it's the along the bedding plane there is little bit of cohesion is there. Suppose you have a foliation plane, there is a little bit of cohesion, right? But suppose you have a very joint which is separated and there is no infilling, then that don't have any tensile strength or cohesion. So that becomes your mechanical discontinuity. So you can see how this, sorry, just a minute. So you can see here how this is in this Himalayan near Rishikesh, you can see the jointed because you know the Himalayan rock are heavily jointed, right? So you can see different joints are there. You can see the joints, right? So this joint, you can see this because of this joint, you can see this can fall. This can initiate rockfall actions. This can fall. So and below this you have road. The traffic is very high because this route is Char Dham route from Rishikesh to Kedarnath. They travel by this route, and the traffic is very high. So even if a small piece of rock fall on anyone, you can imagine what will happen. Right? There are many cases the entire vehicle has gone down or damaged because of this thing. Okay. And as I was talking about damage zone, you can see, suppose you have a folding, right? You have a folding like this. So we have seen, okay, at the center of this folding, the damage is more. And as we move away from this one, the rock type is same. As you move away from this one, the joint spacing is less. So you can see at the core, I have very closely spaced joint. If there is closely placed joint, then the rock mass rating will be less, or it will induce the instability. It will weaken the rock, and once we go away from, then there is increase in the spacing, means the fracture will be less per meter. Then the influence in this core area, the instability will more as compared to the limb area. Okay. So that is why you will ascertain, okay, if this is my regional, suppose regional fold or syncline, I can say I need to evaluate in a proper manner to this central part. Right. Similarly, when I am evaluating any joints, I will see whether the joint is very close, means the separation between the joint surface is very less, or there is some aperture, or there is some opening is there. If there is opening, what is the width and what is the material that has been filled over here? If this is the case, I can say there exists a frictional resistance between the surfaces. Okay. If this is the case, they are not in contact with each other, then I can say the friction will not play any significant role and it may fall. In this case, what will happen? The material we have to see what is the field material that we have. Suppose you have clay field, clay material, clay type material. Then once there is inhalation of water, the clay will swell. There will be slippage. So it acts as a lubricating agent. It's the same thing if the filling material is suppose silica, right? So it adds stability. So that we need to evaluate. So you evaluate as I told earlier, the spacing between the joints. Then we evaluate if there is joints or any discontinuity, whether they are closed space or the open space or they are filled with any material. Okay. Again, I will see, let it be the closed space, then I will see whether the surfaces that separates the two, along this joint, the two surfaces, I will see the roughness. Okay. What is the roughness? Whether they are very smooth, the surface is smooth, or the surface is like this, or the surface is like this. Right. So depending upon this one, we can say, okay, here your resistance will be less, here moderate, here your resistance will be high. So that we need to, that is known as the roughness, joint roughness we call that. Okay, joint roughness. This is we call aperture. spacing between two walls of a discontinuity. Okay. So suppose you have surfaces like this, you have surface like this. So if there is any movement along this direction, this will resist. If there is movement along this direction, then it cannot resist, right? So the shear direction B has more resistance than the shear direction in A. That need to be evaluated. So once you know, okay, this is my plane, and I know this is the roughness, I can say about this. This is example of particularly I've taken this how weathering has influenced the landslide activity, particularly in Eastern Ghat. This is chondritic rock. We have joints, and we can see, okay, there are joints were dipping in opposite direction. For a slope to unstable, okay, I can see if my slope is this, if joints are like this, okay, it will fail. But what is happening here? Then we evaluated this. So we see, okay, the upper part is lateritic, okay, highly weathered, soil is there. Then we have moderately weathered and slightly weathered rock, boulder. Then we have this one, fresh rock. Okay, so this area, top this is lateritic. Then you have this area, right, which is highly weathered to moderately or slightly weathered, right? So what happened? You have a joint. We have joint like this. This is my joint. Okay. So because of this joint, the weathering will be different in different sections, right? So it induces the weathering. So you can see, okay, this induces the weathering. And what is happening? Because of this part, there is joints. It get weathered. The material will be, the characteristic of material will be different. So the strength along the joint is less. So this boulder will come down. So what happens if, because this whatever material you have, if water will increase, then this entire thing may fall on the surface, and that is known as your rock fall rolling down to the track. And we are talking about this rainfall induced landslide, how this water is responsible for your for instability or reducing the strength. Okay, if you have small amount of water, suppose you have sand, and in our childhood we have seen we play with sand. If the sand is the very little amount of water is there, then we can make sand castle, right? To make temples like this, right? So we can make that one. If it is a dry sand, we cannot make that one. So in that way, if small amounts of water is there, then by surface tension they add cohesion to the material, the sand grains. But once the water is more, right, then it separates the sand grains. In this case, you have some cohesion. In this case, you don't have cohesion, right? So the friction will be less. There will be detachment. So what is happening once you have this water, more water? This creates a pressure, pore pressure, okay, and that pore pressure separates this grain. Even during what happened particularly during the earthquake time, when there is a seismic activity, right? Because what happened is seismic activity, there is you have compressions and rarefactions, right? So suppose you have water. Suppose let me say you have water initially. There is no rain. You have this much of water. So the earthquake happens. There will be compression, right? Once there is compression, then what will happen? The volume will decrease. And in that volume, you have water that will be, that creates, that means in a small volume, you have more water now, right? So once there is a shock, compression is there, the pore pressure, because you pressurize the system, the pressure increases, right? And once you know these seismic waves are very fast, the pressure increases, but once it goes away, once this earthquake goes away, the dissipation of pore pressure, means the pressure that was created during this seismic activity, that cannot be dissipated at the same rate as your seismic waves go away. Means, okay, if there is compression and I'm living, there is no compression now, and the pore pressure should drop immediately to the previous. That doesn't happen there, because this is very rapidly we are pumping it. Okay. So that is your cause of landslides in earthquake during the earthquake. So what is happening? We discussed this one. Okay, how this water create pore pressure. Okay, once there is pore pressure, you can see here you have low fluid pressure, means the pressure that is exerted by any fluid that is inside the rock or debris or any soil materials. Okay, that gives the pore pressure. Okay, so this is a plot of Mohr circle, and I hope the geology student they know. So this is something, right? We plot it like this. You have shear stress, you have normal stress, right? And this is your this defines your stability. Means if your conditions, stress conditions, right? Suppose there is a rock, and just suppose there is a rock. This is my stress sigma 1. This is my stress sigma 2. And then I will see, okay, this is sigma 1, sigma 2. Sigma 1, suppose the major stress. This one is the suppose minor stress. Then I plot it. Okay. So if the plot is less than this, suppose in this white case you can see I'm plotting the stress and I see this is below this one. This doesn't touch this circle doesn't touch this line. That means, okay, it's stable. But it has not reached that stress level so that there will be any failure, right? So how this will touch this one? Whether I will increase this one, I will increase this one means the sigma 1 and sigma 3, the difference should be more, means I will increase the sigma 1. Then only suppose I will say, let me sigma 1 lie like this, I increase this like this. Then I can say, okay, now it will fail. Okay. I add sigma 1. So here what happens, suppose you have a landslide, you add more stress on it, you build something, so you are increasing this one. So it will fail. Once it touches this one, that is known as Mohr-Coulomb failure envelope, then it will fail. Or I will simply slide this, the same stress I will slide this to this one, this side. Then you can see this blue, I have slide the same circle of same size that I am moving in this direction. So how can you slide this? So if I reduce the sigma 3 and sigma 1 by the same amount, right? So that same amount, how can I do? Suppose I have something, I have water here, right? If I pressurize, the water will give you opposite reactions, that is hydrostatic reactions to this hydrostatic pressure and that will reduce my, suppose I have sigma 1 here my least principal sigma 3 here, then the net will be here, I will say sigma 3, why this is happening like this, sigma 3 minus pore pressure, in this case my sigma 1 minus pore pressure. So you can see that pore pressure component that is reducing, sigma 1 minus pore pressure, that becomes my effective stress here. So it will slide to this, it will slide by same amount to this, because the pore pressure is radially outward and the magnitude is same, right? So it will touch this one. So you can see initially, you can see this becomes your shear stress. This is the conditions, and it touches this one, and there will be failure, right? So what happens? I have tau, the shear strength is cohesion, plus mu means tan phi, this is the friction part, into sigma n. Now what happened? Because of this pore pressure, the sigma n value that reduces. So this equation is C plus mu, sigma n minus pore pressure. And initially I have like this, tau, cohesion, plus mu, just a minute, it's something which, let me write here. I have tau, that is cohesion I am adding, then I have sigma n, then I have tan. Right, component will be reduced. So my equation is becoming C plus this tan phi means this mu into sigma n minus pore pressure. So this shear strength that was provided earlier is reducing. So tan phi, which is mu. the shear strength is reducing, then your shear stress will be more, and that induces instability. That's why we see rainfall induced landslides. Right, this happens. This is the physics behind the landslides. Then, right? So before rainfall, you can see we have a less pore pressure. Once there is rainfall, then the change in pore pressure, so effective stress particularly decreases there. This is a downslope motion or creep motion. Okay, so suppose you have any material and this is a frozen ground. Once this will be frozen, then it will expand, it will go out off, it will bring the material or whatever the rock or fragments to the top. And when they reach top process, it will fall. So initially it was like it will move like this, then it will free fall like this. So there is a slow moving landslides are there. Okay, this is a creep phenomenon. You can see generally in permafrost region, particularly in Arctic region, you can say what is happening. Okay, in winter you have ice saturated debris. So what happened once there is summer, then the upper layer you have the ice that will melt away, right? And you have at below few meter you have permanent ice and debris. So what happens? Suppose you have the rain, so this cannot percolate into this one. So the entire medium will get saturated, right? With your this with thaw process, with melting of this ice. Because the ice cannot go infiltrated into this one because you have ice and the permeability is reduced there. The entire thing that will flow down. Okay, the entire thing will flow down, and you can see there are landslides in permafrost region. The effect of bedding, you can see the effect of bedding here. You can see here, okay, there is, suppose you have a heavy rain, suppose you have limestones, you have a layer of shale, and suppose you have sandstones here. So what is happening? If there is any rain, okay, it will percolate into this one, and we know that this shale is impermeable, right? That means the material that is coming over this, the rain that is coming over this, the water cannot infiltrate into this ground. No? Because you have a shell that is impermeable. So whatever rain it receives, it will saturate the mass. Suppose this is a sandstone. Generally, sandstone should be better than this shell. But because of this impermeability, you have more water here. So this entire mass will be saturated. Then it may happen. The material will go down. So you can see this material. Okay, this material that has blocked this part. So suppose you have any river that is flowing, so we are bringing artificial dam to that one, and once the water level rises a certain level, the entire dam breach. When there is landslide, it creates an artificial dam. Again, with water, the water level rises because you have block, then the entire mass will fall. This type of thing happened in Gajapati district, Badagaon, where I think 12 or 13 people died. Okay. Let's talk about prevention. These are the few causes that I am talking. Then about this prevention, if you see, suppose this is a natural stage landscape that is before construction, and we build something. We build something like this. Okay, I need a house, so I have to flatten this one. I have to do this. I have to cut this slope. I have to make the road here. That is my infrastructure development. I will make a road. I will cut this slope. By doing this, what I'm adding load to this one. I am doing whatever initially you have a sloping surface, whatever water you have, that it goes down on the surface runoff. Because you have made it flat, so what will happen? The more percolation of water into the material, into this one. And you have a gentle slope earlier, you make this because you want to make a road, you make a steeper slope. Right. So these are the construction activity because of which we got landslides. Sometimes we try to put mitigation measures, but what happens if you suppose this is a mitigation measure? No doubt it will support this land to move, but if you don't put the pipe for drainage, then the water pressure are blocking this one. The water pressure here will be more, so then there will be landslides. So whatever water pressure is there, that should be dissipated, that should be discharged out. Okay. Sometimes, many times, the landslide occur because of lack of maintenance. This is blocked, and no one is uh, thinking about this. Okay, this have to be maintained, and there is, if this you have these pipes, you have drainage channel, but you are not maintaining it. Similarly, you can see, okay, these are the suppose these are the foliation or joints or discontinuity. I will say we want to build a road. So if I build a road in this direction, we know, okay, these are the joints that is there. So it will induce instability because these are dipping or the slope is gentler in this direction. It will add instability to the slope. If you are going in this direction, you can see, okay, this joint dipping in opposite direction. So this will be a stable part. Okay, that we need to know while we are preparing for any development work. These are few examples from this Himalayan region. We know Himalayan rock is very fractured, highly shattered, fragile in nature. There are many joints. So you can see these overhanging mass, this wedge failure, the joint that contribute to the instability. These are few examples how these blocks and the jointed rock mass fall. You can see these are the jointed rock mass that fall because of this toppling effect, because of this joint. Suppose I want to, okay, let me make a bench so that this slope will be stable, right? If I have this type of slope, so what will happen? The material will slide over this, the material will slide over this. Okay, I know these are the joints. If I make parallel to the dip of this joint, right? If my benching is this, then there is no chance there will be sliding. If I make a steeper slope, steeper bench, this mass may fall. Right? So bench rock slope, both are benched. But why this fails? Because, okay, we have not taken into consideration of the discontinuity, dip of the discontinuity into considerations, right? We have done a study. We have taken out different slopes. We have reduced the slope angle, right? I mean, suppose 70 degree initially, we have 70 degree, and you want to know what is the factor. This SRF is strength reduction factor, which I told you about this factor of safety. And the factor of safety, if it is more than 1, it is stable. So it is a 70 degree slope. Let me make it 65, only 5% reductions, right? And I benched it. So my factor of safety increases to 1.47, means more than 1, it's stable. So once I gentler the slope, I make benches, then this becomes means this is stable. This should be addressed. These things should be taken into account. Okay, up to what angle the slopes are stable. If my rock type is this, then I can go up to 60 degree. Suppose my rock type is this, then I can go up to 50 degree. That should be studied. And if you do this, then you substantially reduce any anthropogenic or construction related landslide. So we do stability assessment, we do for rock slope, we do for debris slope. Yes. Hello.
प्रीवियस स्लाइड में एसआरएफ बोला तो एसआरएफ माने कौन?
एसआरएफ माने हो स्ट्रेंथ रिडक्शन फैक्टर हुई जोटा कि तुम फैक्टर ऑफ सेफ्टी संगे समान. फैक्टर ऑफ सेफ्टी मु कम कहिथली, फैक्टर ऑफ सेफ्टी इज your resistive force divided by your driving force. So when resistive force is more, that means if it is more than your driving force, the factor of safety will be more than 1. So any value that is more than 1 is stable. So this is the SRF is equivalent of factor of safety. This has been used for this. There is a simulation model. There is a different model that I will talk later. Strength reduction factor means if I will reduce this slope, if the strength parameter is reduced by 1.47 times, then there will be failure. You imagine in that way. If the slope, the characteristic of the strength will reduce to 1.72 times, then it will fail. So in that way, if once the values are more than 1, higher the value, the stability is more. Is that clear?
Yes, sir.
So you see the stability assessment, you have rock slope, you have debris slope. So you have different types, rock mass classification technique, like I told you, like RMR, SMR, then means rock mass rating, slope mass rating, geological strength index, continuous slope mass rating, you have Q slope, right? There are many. So that is one of the classification system from which you can know the health of the rock. Then we have kinematic analysis. This kinematic analysis, it plots the different discontinuity and a slope plane, and we will see, okay, this structure, because of this discontinuity, will there be any failure? Then we do numerical simulations. We took many parameters into considerations, and we took limit equilibrium analysis, finite element modeling. Okay, so that we do. I will show you few examples. I will do. And debris slope, of course, we do limit equilibrium and other modeling. But this is generally we do we do rock mass classification, kinematic analysis in PG level. The numerical simulation generally in PhD level we do. Okay. So criteria for landslide investigation. So we need regional scale approach, local scale approach. Okay, regional scale approach. You have many remote sensing techniques that can be used. Okay. And regional and in local investigation, you need what are the locations, so what is the type of slide, where is the fracture, what is the type of material. So very detailed study of a particular slope. Okay. That is your local scale investigations. Few examples that I want to show. This is also in the Himalayan region. Okay, and I have chosen this because this is very close to this IIT Roorkee, particularly from Rishikesh to their flag. In that section we have done. So here you can see this, as I talking about this failure of this slope, the entire mass, the deep is, the slope is in this direction, the deep is in this direction, dipping opposite to this, there will be rotation and falling, toppling of this material. So we plot it. This is your kinematic analysis. What happens? We have a slope like this. We plot the slope in the stereogram. Then we plot different joints, and I have friction angle, right? So I will plot this. Then I will see is there any chances of failure. The example you can see here. This is a planar failure. I have plotted the slope here. Okay, I plotted the slope here. I plotted this joint. Okay, this joint is gentler than the slope. And the friction angle, suppose friction between the metal that we are talking about. So the joint should dip more than the friction angle, but less than the slope. Okay. So anything that lies between this, anything that lies between, you have this is deep of the slope, this is your friction angle. So this part, I will say, if anything in between this means the joint is dipping more than friction angle and less than slope, this is danger. This induces instability. Similarly, if you have any wedge like this, so we see the hinge means the intersection between these two. So I have slope. This is the intersections. This is my friction angle. That means it will induce instability. So this is how structurally controlled landslides or rock slides are evaluated. This is I have shown you how these joints are creating problem in this region. You can see this is a type of wedge failure here. The joint intersects and they induce the instability. You can see you have a rock mass like this, and you can see there is a traffic. And if this block will fail, then what will happen? It has fallen and it has taken this barricade from this side to the river. Here another example we have seen you can see at the top of this slope, right, there is a tension crack, means there is fracture. And this fracture, what happens, whatever you have material, whatever you have water or infiltration of water, the rainfall, that goes into this. Once this goes into this, the water pressure here increases. So you can see initially in July 2017 it is like this, and when visited in September, because of this tension crack and the water, the entire mass that fall down and block the road. This is the similar case. Here you can see this crack probable failure zone that has initiated instability and there is failure. Now this is a concern. Okay, I don't know whether I should talk about this, but when we are doing any road widening activity, you are excavating the slope and you are dumping this material. So by doing that, if you are not identify a proper site, you are reducing the width of the river, the flow will be different. Okay. Then you are blocking the drainage, so this may create problem. So that also need to be checked. You can see here there is, suppose you made drainage and you have a slope and we don't drain this water, it will saturate the mass and there will be failure. It will saturate the mass. You can see how this water is coming. There is seepage and there is collection of stagnant water. Okay, so that water is one of the main culprit that induces instability. So how we do that finite element modeling that we are talking, we take the properties of the rock mass, different property we took. We take, okay, this is the debris you have, then we have fine debris you have, then we simulate the slope and we find, okay, this is the slope where there is this shear stress and more, so this mass may fail. So this becomes my failure surface. And once this fail, the road will be blocked. Right? This is how we do simulations by taking different parameters. This is one of the landslide in Himachal Pradesh, Kothrupi landslide. What happened? You see, what happened here? There is a stretch of around, I will say, this is the landslide, and this is the national highway that we have. And here there is a tea shop, right? A tea stall was there, and it was around a night 1:30 like that. Okay, so they stopped here. The bus stopped here. The passenger all took the tea. They waited for around 10-15 minutes. Then they started moving this side. Another bus was also coming from this side. And just at the, you see how unfortunate they are. At this point, when they are at this point, the entire bus slided down and almost the bus went up to 2 to 3 kilometers down the valley, right? And I think how much 46 people killed in that tragedy. This is one example how sometimes this unfortunate thing happen, and I can give you another example. Some things, the lucky breakfast, right? So there were a few passengers in a bus, and they stopped somewhere to take breakfast. So there was no one in the bus. A big boulder came and it hit the bus. So sometimes because of this, they one from breakfast they were safe, right? So they are fortunate. So this is the slope. So we have seen, okay, there is a fault. This is that Kotropi landslide. Initially, you can see the remote sensing image. You have very little scars out there. Okay, in 2017, before 2017. Then and you can see how this landslide, a very big landslide. This was a very big landslide. So we have investigated this one. We have taken the rock and soil sample. We have done resistivity measurement. We have taken the different slope profiles, right? And you simulated. You can see this at the thrust zone, and this is the fault rock. In that we have fault rock. I can see. Okay. So we do this type of test in laboratory. Okay. We do a geophysical investigation. This is a electrical resistivity tomography, right? The material that we have different resistivity. Different rock have different resistivity. The debris has a different resistivity. If that is water saturated, that has a different resistivity. So we have different electrodes that we put. Then we see what is the resistivity, and depending upon that resistivity values, we can say, okay, up to this much, this is debris, then this is the saturation zone, then we have rock. So we can suppose this is the slope, this is in Nainital, we have lake, and the resistivity value, we can say, okay, this is my, suppose let me this goes to my debris. I have then fresh rock, then this patched debris is water saturated. So I can analyze, okay, I have to take this is debris, this is what very high moisture saturated mass, this is my bedrock, so I will do analysis for this one. So we do 2D modeling analysis. When we do, okay, we put different materials, this is different materials we show, this is a fault that is thrust that is there, and there is a different material, I have debris, then I simulate this one, I find, okay, this is the mass, this is the stress it is showing, so the mass may fail. Okay, so we do analysis like this. The same thing, 2D, 3D analysis can also be done. Like this is for the same area we have done the 3-dimensional analysis, right? So why I am showing this one, in assessing the landslides, advanced versions of software you may use, and you can do your study. So we have different rock. Okay. Then we build a 3D geological model, and you can see. Okay. In dry condition, my displacement is concentrated in this one. Once this is saturated, then the displacement is concentrated in this mass. There is more concentration, the red part is there is higher displacement. Accordingly, suppose if you want to put the sensor location, as I told you, because the day for this disaster risk reduction, okay, and UNO want, okay, within next 5 years, there should be sensor deployment. We should have proper, early warning information so that we can mitigate the things. We can escape at least, right? Okay, there is some activities going over, so we should be very careful. So this, once you know, okay, I have done the analysis, I can put the sensor, okay, the information, because this is the displacement I want. Okay, if anything will happen, if I will put the sensor here, it will record. If something I put here, the instrument, it may not record, right? It will record at a later stage when everything will fall. So that also proper locations can be also identified with this model, right? So these are for the saturated conditions. So different sensor can be put. This is an example of this Koraput Rayagada landslides. That track is very much affected by their landslides, right? So we have visited this. There are many landslides event that you can see. As I told you, this is the cause because of the weathering. These landslides is there, and the lateritic, that this, when there will be water interactions, it becomes very plastic, right? So as I told you, so when you simulated, okay, the joints are dipping like this. So why they're dipping in opposite direction? Why they? Because the weathering is different. This mass will roll down, this will fall, right? This will fall like this. This is happening. What is there? Landslide dam burst in Odisha. This happened in Baraga in Gajapati district. And what happened? There is I will show you in next one. Yeah. This is the slope, you can see. So this is the slope profile. You have boulder, you have your layer. Here you have a cave, right? You have boulder, you have soil. This is your chondritic fresh rock, right? So few people, because of this rain, this is because of the Titli cyclone. Okay, so few people were there. They find, okay, these caves might be safe for them because of this heavy rain. So they went and they took shelter here. What happened? With increase in rainfall, the mass that come, and here you can see there is a cave and this is a flat surface. They came and here it became it got deposited and it became an artificial dam, right? Then the water level rises, right? The water level rises. So it was saturated, the entire thing. Then it come to here. There is a failure from at the top down portion. The material came down. The material blocked here. Okay. Once the metal, there is artificial dam. Then you have your water that is coming over this, and it will get filled with water. Once this is incapable, because by its weight only it can retain this water. When the water is enormous, then the entire mass that will go away, and because of the gyrating, the water enter into the caves. It reaches the dam. And took away the lives. Okay, up to 12 or 13 people. So my concluding remark to educate the people, we have proper participation. We should develop early warning system. Real-time information should be given to the people. So as a student of this earth science, including geology, geography, environmental science, if they can educate people, if they can understand, if they can do something for this research, any research, not only in landslides, other hazards also can take, so that our economy can be saved, people can be saved, and the environment can be saved. So if you want to live to work for another day, then you have to manage the disaster today. So that is my concluding remark on this. And thank you all. And if you have any question, you can ask me.
Thank you so much, sir.
Thank you. Thank you.
So now this is open for discussions. If you have any doubt, you can ask students. କିଏ କ'ଣ ପଚାରିବ ପଚାରି ପାର?
ପଚାର ପଚାର।
ମାଇକ୍ରେ ମାଇକ୍ରେ ପଚାର।
It was it a long talk? It's okay.
It's okay, sir.
No problem, sir.
It was a nice.
Sir, how can we predict the landslide before it happen, and so you can reduce the death, and also how can we control the landslide?
Yeah. So regarding prediction, you see, if anything happens, that gives very early signature, right? I have shown you a few examples. There was a tension crack above a landslide mass. Okay. So let me see if that is a tension crack. If I put some measurement there, suppose I will say what is the pore pressure there. Let me measure that one. So the pore pressure is increasing. I can predict, okay, there is chances of landslide. Suppose I will put any displacement sensor, which will give you, okay, if this is the displacement sensor and the data that I am receiving, if there is some movement is there, then I can say, okay, this is translation activity there. There is some down motion is there. I need to be very careful. Suppose I will put rainfall. Suppose there is rainfall in this landslide. I will establish an equation. I am taking that, okay, these are the properties of the material, and I saw, okay, if the rainfall go beyond this within this time, then it will be disastrous. So that rainfall threshold I have to see. So there are different parameters. Means somewhere we put soil moisture sensor, somewhere we put piezometer, somewhere we took the deformation in LIDAR survey, right? So all these parameters should be done, and if anything is happening, any threshold is crossed, then you should be very alert and you should send signal, okay, alarm, there is a landslide and there might be any activity, so you evacuate that. So that is why we will do that. Apart from that, we can do stability analysis. Suppose you don't have anything, you take samples and log and do the analysis, and you say this, well, so we should not construct anything, or we should treat the slope. Okay. And this is your first question regarding this early warning, how you will predict. Then you have your how to mitigate. There are many mitigations measures. Suppose simply the things are either you reduce the shear stress there, right? So slopes should be gentle. The first thing, I will put some benches. Okay. So these are some you can take. Apart from that, suppose you know, okay, there is there underlines and the raw right, so I will hit that wall and so that is done. There are something. This is the mitigation. Something we should avoid the landslide. Suppose there is rock fall in a place. So let make a tunnel. Whatever material comes, it will go away from. It will drop on this tunnel, or it will go away. Then you can travel through that one. So there are many measures. software. Then you have finite element modeling or finite difference modeling softwares. Okay, these are you have rock science software, RS2, RS3. We have Flag 2D and Flag 3D. We have Plaxis software. So it depends on how what is available and how we are doing that. So there are many. Even you can also prepare your own model and generate in simply Excel file. Also, you can do that. Generally, I am using RS2, that is rock science software. Generally, I am using that one.
Sir, during modeling, sir, what type of data we have to collect from that landslide to input on that modeling?
The very first is for landslide analysis. First, you take the what is the slope. The morphology of the slope is very important. Then you identify the rock. You identify the joints, right? Once you identify those things, then you bring the rock sample or you test it in the field, right? You take, suppose you do a strength study. What is the shear strength of CI? What is the elastic parameter of the rock? What is the Poisson's ratio? What is the elastic modulus of the rock, like Young's modulus, right? What is the density of the rock? These are the input parameters. And you have to take the joint parameters. What is the friction angle of the joint? Okay. So you make a slope. You insert your different layers, put different property to that layer. Okay. Then you simulate it. Then you will see what is the factor of safety it is giving, where the shear stresses are more, that you can edit.
Okay, so sir, one last question.
Yeah.
Sir, you have told so many names of the software. Sir, is there any open source software? All are paid? Doing sir primary work.
Mostly paid softwares are there. These are paid software mostly. But I can share you some Excel file that can be that you can use in this study.
Okay, sir.
That I can share.
Please, sir, please.
Even if you want to do really analysis, I can provide you my software. You can remote access those things, right? You can do the analysis from there also. And this Professor Asim Amita Pradhan is my batchmate, right? Right.
Yes, sir. Okay, sir. He is also my guide, sir, MPhil guide. So you can share him, then I can go.
Yeah, I can share you. Even you can come to IIT Roorkee and you can do analysis. You welcome. Okay, so
Okay,
anyone,
sir.
if you want to do any help from my side, that will be provided with open heart.
Thank you, sir. It's a very honor from you to getting these words. Thank you so much, sir.
It's my pleasure. It's my pleasure.
Thank you, sir.
Thank you.
Dr. Durga Prasanna Mahanti has raised his hand. He may ask some question.
Yeah, hello, sir. Namaskar.
Namaskar.
Hello, everyone. So I joined late, so I'm sorry for that. I had a lecture actually,
Oh,
so I could attend the last part of that. So I hope my mic is audible to everyone.
yeah, you are audible.
Okay. So I just had a query. It's not a question as such, but just clarification I just need. You have shown that simulation towards the end of the lecture,
Yeah.
and for different kinds of rock types, or there are landslides in northern states, like in Himalayan case. There are landslides in as you have shown in the eastern Ghats, and there are also the cases in Western Ghats, or in Maharashtra we have landslides. The rock types are definitely they are different. So how do you see that the difference of the slides? And while doing the simulation, do you see any challenge if the rock types are different? Do you have to give some extra efforts, or some kind of different methodology or mechanism you need to apply for this kind of modeling? I hope,
Yeah.
yeah.
Thank you, Professor Mahanti, for this question. So let me see. We have Himalayan region, we have Western Ghat and Eastern Ghat, right? And Himalaya, there is active tectonics, and the rock is highly fractured. There are many joints, right? So really, it is very difficult when we are simulating Himalayan slope, particularly rock slope, right? Sometimes, suppose you have a very larger plane which is failing, along which there is failure. That is means everything is suddenly quite difficult. Then you have to reduce different parameters.
experience as we are working this terrain. As you have explained during our water pressure slide, that seismicity has some role. So towards as per the land side is concerned. So my just simple question is that, or you can just enlighten all of us. So let us in Himalaya terrain, or it may be northeastern terrain where our seismicity is quite encouraging or quietly effective. And if it is so, and if it is triggering the landslide process, so is there any, in today's modern world, is there any new technique as a result, so we can deal seismicity for the mitigation of landslide in a better way? So if you can throw some light on it, so it will be our pleasure, sir.
Thank you, Muthunya, for your kind words. Right? It is a long time that we are talking. So we are talking seismicity. We know that, okay, seismically very active this Himalayan region. So what happens when there is any seismic activity? Clay slope, what happens in clay type material or very small? We have less permeability there, right? So what happens when there is any seismic activity? It will compress the system, right? So the is compressed, the water pressure cannot be disseminated in. Suppose I will say there is within microsecond it increase to manifold, but for the decrease it will take a long time because there is the permeability is very less, right? So it cannot, the water cannot escape out from the system. So if this is the case, we should do proper drainage in that area, so that if anything is happening, then that can be the increase in pore pressure can be decreased. Then suppose you want to mitigate this landslides. This is about where liquefaction, this process is liquefaction that I told you. And if you have, want to do any mitigations measures where there is any slide, then we do seismic stability analysis, right? The seismicity coefficient is taken into consideration while designing and analyzing the slopes, right? So something is stable at present conditions when you are in seismic condition, when you are stabilizing that, and you have to take the seismic coefficient depending upon the different seismic zones, and we put it into the model, and we establish, okay, this is the factor of safety that is coming, and this is my mitigation measure that is providing, and the mitigation measure, suppose I am putting any retaining wall, the retaining wall, suppose the factor of safety is this much, let me see at this much of seismicity, what should be the factor of safety of my retaining wall. So these are mainly the concern is, I will say, whenever there is earthquake, it happens mainly of liquefaction that I told. Rockfall can be because you have a detached mass, and any vibration that goes, it can initiate this rockfall.
Okay. Thank you, sir. It was a very nice conceptual explanation again, and hope so we will meet soon, and you have also field trip towards.
Actually, I went for a field trip in Assam, but it was so packed, right? I went up to Enisak.
Yeah.
And it was so packed I could not meet you, and I am really sorry for that. It was like we started from 6 and it ended at 8 in the evening, right? So definitely.
Okay, no problem. So we'll definitely meet very recently, and you have with your students. As a result, we should gain some experience from you also. We should gain some expertise from you. And again, my thanks to all the co-faculties and my friend. So for arranging this PPT and as well as just inviting you, sir. Thank you all.
Thank you.
Thank you so much, Mrutyunjay Das. Now one question from our student. Yes.
Good afternoon, sir.
Good afternoon.
So as we know, landslide is a very rapid and quick action. So how feasible will be the warning system? And at present, what are the infrastructure or warning systems at present?
Okay.
Except seismicity.
Okay, so we know that landslide is very rapid. There are landslides which are slow also. It's not always landslide is always very rapid. If it is creep phenomena, it takes many years to initiate any significant mass movement. So that can be observed, right? If you have debris slope or soil slope that I told you, it gives prior signal, right? There must be some, I will say, deformation in the ground, right? There must be something, this soil moisture increases. There must be something that the pore pressure increases. So if we measure these things, right, these parameters, and we know, okay, this is the threshold, we have to establish the threshold depending upon the material properties. Once that threshold is crossed, then we can say, okay, there is chances that there is some activity and we can send the alarm. The difficulty arises in rock, right? Because rock is very rapid. That is very, means I will say many work is still going on for this rock slide early warning, and still I will say we are in a very juvenile stage, right? Because it is very difficult to predict.
That means we have to study before landslide. That means we have to pre-feasible study that area and classify it under landslide prone area.
Yes, that we have to do, and we have to take. Suppose you identified this. I think this is the slope. These are the parameter. I think this will be vulnerable. So I will do the analysis. I will say, okay, the factor of safety or the stability condition is like this. There might be failure. Then we can say, okay, then stabilization measures will be taken, right? So that can be done, and this early warning for soil debris slope that is well in advance, and that can be done. Many research is going on for this rock slide particularly. It's difficult.
That means as of now there is no such technology to.
There are technology, but not widely, I will say, used, right?
I'm asking, except seismology is there. You can detect by seismic study, but except seismology, what else do you have?
Pardon?
We have seismic study, or we have seismicity, by which we can easily find there is a seismic activity and this landslide prone area is going to affect it. But except that study, what else? What another technology we have to prevent? We have to issue warning signs to local populations.
You see, for this seismic you are talking about, age we are unable to predict the exact, means unable to predict or give alarm for this earthquake. It becomes difficult. You can give it for tsunami, but prediction where it will occur, when it will occur, that becomes difficult. Of course, we can detect the waves after it happened, right? So in landslide, what happens? We have to detect something before it happened, right? In seismic, what we are doing, something happened and we are detecting. Then we are sending, okay, the P wave arrives first, the S wave arrives later, then the surface wave arrives later, then the signal, the P wave arrives. So you will say, okay, this wave is arriving. You can get, at least I will say, if the epicenter is, I will say, at a distance, then you can say about that, okay, there is landslide.
Okay, sir. Thank you, sir.
There is a but in landslide, it's become sometimes difficult, particularly rock. There are, okay, you can say, okay, there are fracture, there is increase in pore pressure, there are a few parameters which you can take and do that.
Thank you, sir.
Okay, thank you.
Another question from another student.
Good afternoon, sir.
Good afternoon.
Sir, how can we determine the accuracy of any landslide hazard zonation on map or model?
Accuracy, it's you see, it depends upon the tool you are using, right? So it depends what is the resolution of your data. So as the resolution is more, you will do more. You will more confident about that. So you are doing in 1:20,000 scale, you are doing 1:50,000 scale, or we are doing in 1:2 lakh scale. So in regional scale, if you are doing anything in a regional scale, suppose I will see, suppose the entire state of Odisha I will see, then you will take the help of remote sensing and GIS, right? But what happens when we are doing any regional analysis, this slows generally the landslides that occur, suppose a 50 meter, 100 meter, 30 meter stretch, right? So it becomes difficult when we are doing that. Bring the data and do the analysis. And you can correlate this with your existing model, and you can give a susceptibility.
Yes, sir. Sir, what are the methods to calculate the volume of landslide debris?
Yeah, this is a very good question. There are many methods involved. Suppose just I'm taking the basis of this one. Suppose you have a very fine scale contour map, right? And you identify, okay, this is the probable slip plane. So you have the contour map. This is the slip plane that will occur. Then you can say, okay, slip plane. Slip plane. So I have the elevation difference of each point from slip point to the existing slope. ठीक है? So this is the height difference, this is my area, then I will integrate everything. This is length, this height, then I will integrate. Then I can say, okay, this much amount of mass will dislodged. So that we can calculate the volume of the slide. Existing slope भी करी हबो आउ जोटा फेल्ड हो जाई तारे भी करी हबो कारण मटेरियल जा भी डिपॉजिट हेबो again it will change the contour pattern of that area. So you have a Pre-event, you have a post-event, you compare that and you will get that one.
Okay, thank you so much. Is there any more question? No? So thank you, sir. You have taken the class elaborately and taking almost 2 hours. So you have given your precious time for us. So now I request our colleague Arun Kumar Naik to give the formal vote of thanks.
Thank you, Dr. Asim. A very good afternoon to one and all present over here, both offline and online. And I am Mr. Arun Kumar Naik, Assistant Professor from Department of Geology. And I feel very privileged to offer the heartfelt thanks. And on the behalf of Geology Fraternity, FM University, I extend my vote of thanks to our today's chief speaker, Dr. Sarada Prasad Pradhan, for gracing the lecture series by sharing his knowledge and findings on landslides in India in geological perspective. And I am very much confident that after attending this lecture, our students had a clarity on application of stress, strain, and other kinematic parameters in landslides, and also they had knowledge on the various geological considerations while constructing various engineering structures like building roads and bridges. So thank you very much, sir, for sharing your knowledge and elaborating very clinically. Thank you, sir.
Let me thank you for inviting me for this lecture, right? So it is always my pleasure to interact with you all, right? It's a platform to exchange knowledge, to discuss something, right? So this is how you educate ourselves. So we means we are teachers because students are there, right? Okay. So we learn from the students too. So it's really very good, and the interaction was very nice. And I hope that virtual lecture series that we are conducting as we started from today will be successful one with time, right? And definitely whenever I will get any opportunity to interact or to come to FM University, because you have a very, I will say, recent department, but you are doing many activities, right? As I learned from Professor Asim also. And that's really great. Means there are many universities in Odisha ahead of them in this year, right? So thank you all. Thank you all the students for listening this.
This is the first ever lecture series in our department, and you are the first ever speaker.
So that is, I'm very grateful to you. I'm very grateful. I feel honored for that. Thank you.
To listen more lectures on different aspects of geology.
And also, we are inviting you, if you are in Odisha in some days, then please come physically.
Sure, definitely. I may plan in December, and definitely I will visit.
Okay.
Thank you, sir. We may, sir, collaborate with you also.
Definitely, you are always welcome. I mean, your students, they can come if you want any help, any test you want to do, any help you want to do. You just tell me whatever help that I can give, I can assist.
Thank you.
Another thing, can we collaborate in any student exchange program?
Yeah, definitely we can do student exchange. I don't know, but yeah, dissertation can be done. For student exchange, there is MOU is required. Yeah, but dissertation we can do. Okay. Summer internship we can do. Dissertation we can do, means I can be co-supervisor. I can help even if there is no need of co-supervision. I can help. There is nothing.
Definitely.
That is everything. Whatever is here, it will be provided to you.
Thank you so much, sir.
Thank
also, we are thankful to the audience. Without the students, without them, the program cannot be successful and interactive. Thank you all. We also thankful to Google also, because Google also is the platform, so that we are away from each other and managed to complete this program.
Yeah.
Okay, thank you also to Durga Prasanna Mahanti present here, Suman Baral also here, and Mrityunjay Das, Sabita Madam also here, and all other students. Thank you, thank
Yes.
you.
Suman is here.
Yeah, Suman Baral is there also.
Suman. Okay, he might be off. Yeah.
No,
Okay,
I am
then.
here. I just joined later.
Okay. So,
Hello, sir.
Suman is also doing a very good work in this landslide study. He is in NGF, National Geotechnical Facility. So he has blend of both geotechnical and remote sensing part.
Okay, sir. Thank
Yeah.
you, sir.
Thank you. Goodbye.
Okay, thank you.
Stop.